Welcome to Unit 2, Lesson 5, Applications of Quadratic Equations. So some of this might feel like review of some things that you learned last year as well in grade 10, but we're going to, of course, apply some of the newer concepts related to radicals and things like that to this as well as we go through it. So one common example that you would have seen a lot in grade 10 last year is the path of something that is being launched in the air. And in this case, we are tracking the height of an object that's thrown off the top of a cliff, and after t seconds, it's given by the following equation. So h, the height, is equal to this equation here. And we want to use the discriminant, actually, to determine if the object ever reaches a height of 110 meters. So this first question is a bit of an interesting one because we don't actually want to solve for a specific time or a specific height. We're trying to see, is there some possible time where this actually does cross a height of 110 meters? So in other words, what we're trying to do is see, is there some time, is there a t value that occurs if our h value is 110, or in other words, is there a time that exists where our height is actually 110 meters? Well, in order to do that, once I reset this, in order to do that, all we need to do is substitute in 110 meters into our equation. So 110 as the height is equal to negative 5t squared plus 20t plus 80. So in a sense, we could think of trying to find a specific time, but more generally, the question is just asking us, is there ever going to be a time when this does cross 110 meters? So really, we're looking at an equation like this and asking ourselves, not even to find a specific solution, we're just asking ourselves, does this have any solutions? And if it does, how many? So that's where we're going to use the discriminant, because remember, the discriminant is something that doesn't solve equations for us, but it tells us how many solutions are possible, and most importantly, if no solutions or real solutions are possible. So if we rearrange this, first of all, into a standard form, I'm going to move every term that I have on the right over to the left side, and that's going to make my t squared term positive, so positive 5t squared minus 20t, and then I combine the two constant terms together. On this side, they would be plus 30. So to put that into quadratic formula, we would need to recognize that our a value is 5, our b value is going to be negative 20, and our c value is going to be 30. But we actually don't need to use the full quadratic formula here at all. We just need to use our discriminant and see what it tells us. Our discriminant, remember, is b squared minus 4ac. So that's equal to, well, negative 20 squared minus 4 times 5 times 30. Or in other words, that's like 400, subtract 600, and we actually get negative 200. So the 200 part is not so important. What's really important to notice about this is that it's negative. It's a value less than 0. So now we can make a really important statement, similar to what we did when we were first learning the discriminant. We can say, since b squared minus 4ac is clearly less than 0, therefore, there are no real roots. And because we can't really accept imaginary numbers as values for time, we can only accept actual real numbers for time. That means there's no real point in time where this object will reach 110 meters. So we can therefore say that the object will never reach 110 meters. So that's sort of more a general question that we can answer. Now let's try and answer something more specifically. This second part is asking us when specifically, exactly when, does the object hit the ground? So again, when we're trying to find when something happens, that word when should trigger the idea of time in your head. So once again, we're finding a value for time if, well, what's our height going to be in this case? Well, if it's hitting the ground, we can hopefully agree that the ground has a height of 0 meters. The ground is 0 meters above the ground. So 0 is equal to negative 5t squared plus 20t plus 80. And now we could actually find our a, b, and c values straight from here, but we should always try and make them as simple as possible before we use quadratic formula. So remember that you can also common factor out first. So it's always best to common factor out anything you can. And so I'm going to common factor out a -5 because everything can be divided by that. That leaves t squared minus 4t minus 16. And now I can just use what I have inside my larger bracket that I just created as the actual values that I'm going to substitute into my quadratic formula. So in that case, my a value is just a 1, my b is -4, and my c is -16. Take a few minutes now and try and work through the quadratic formula, and then start the video back up again and see what I've put in as mine. So I'll show you eventually my full solution and talk about the answer, but I want you to just try this independently first, and then I'll jump in to show you mine after. So here's what I got. In the end, I found that t was equal to, once I simplified it all, and this is where we're going to make use of all of those radical skills. We're not going to round this off using a calculator or anything like that. So I got 2 plus or minus 2 root 5. Well, as usual, that means we really have two separate possibilities, so we need to look and think about each of them for a moment separately. So we could say, therefore, either t equals 2 plus 2 root 5, or t equals 2 minus 2 root 5. But if we think about this second one for a moment, 2 multiplied by root 5 is going to be a number larger than 2. So in other words, we're taking the number 2 and subtracting this piece, which is bigger than 2, which means overall, this whole solution here, that the second solution that we found, is actually totally negative. And you probably remember from grade 10 that if we end up with a negative solution for time, we're going to ignore that possibility because we know in reality we can never have a negative value for time. And so even though it's something that popped up mathematically out of our solution, it's not something that connects to the real world. So we use a fancy math word and we say that this one is inadmissible. And inadmissible is just sort of a fancy word for saying not allowed or not accepted for what we're trying to do. So that means really we just have one specific value to worry about, and I'll use that for a therefore statement. I'll just use the space up here. We can say therefore the object hits the ground, and this is where you're going to sort of do a double take for a second and go, wait, what do I write down for the number of seconds? Well, the number of seconds it takes to hit the ground is actually 2 plus 2 root 5. So that is one single number. So we can say the object hits the ground after 2 plus 2 root 5 seconds have gone by. For this next one here, we've got a triangle where we don't know what its base and its height exactly are, but we know that the base of the triangle is 2 centimeters more than its height. And we know the area of the triangle that we're trying to make this all fit into. So let's try and find the exact length of the base if we can. So draw yourself a little triangle. It's got some height to it. And I'll define these off to the side in just a moment, but I'm going to call it x. So the height of the triangle is going to be x. And that means the distance along the bottom, this base, must be 2 more than that. So I don't know what x is, but I know that whatever the base is must be x plus 2. So if that's x centimeters, then this is going to be x plus 2 centimeters. And let's just define that up at the top. So we're going to say let x represent the height of the triangle. And that means x plus 2 will represent the base of the triangle. And now let's think about where we can go from there. Well, the only other piece of information we're told is that the area is 5 centimeters. So let's try and construct some sort of equation based on area, because then we can substitute in a specific value for the area. We can substitute in a 5 in place of a for area. And if we think back to what we know about triangles, we know that area of a triangle is half its base times its height. Or in other words, you could also do it as base times height divided by 2. But now we want to replace everything in that general formula for specific things in our question. So we know what the area is, it's 5. I'll leave the 1/2 out in front, but the base from now on we're going to call x plus 2, and the height we're going to call x. So that means we have to do a little bit of expanding. If we want to simplify this into more of a regular standard form quadratic, so these would multiply to be x squared plus 2x, and now I'm going to multiply the 1/2 into everything. So 5 is equal to 1/2 x squared plus x. But when I work with fractions in an equation, there's always a way I can get rid of fractions. And that would be just by trying to find something I can multiply both sides by the same thing. So if I multiply everything on both sides by 2, then I end up with an equation that is still equivalent to what I had. But now I don't have any fractions. And so if I rearrange this, it's a much nicer, proper standard form quadratic. So what does that mean? Well, this is where I'm going to leave it to you to finish off, but just remember that means we now know our a value is 1, our b value is 2, and our c value is -10, and we are just trying to solve for a specific value of x. I'm going to leave that for you to try and finish off. I'm not going to go through the rest of it in this video because it really is just using quadratic formula. So once you've used quadratic formula and tried to solve it for yourself, go and look at the completed version of this lesson to fill in and make sure that you've done it correctly. And once again, the correct answer may be something that uses a combination of a whole number and a radical portion added or subtracted with it. So just keep that in mind. It may not be a nice, simple fraction or whole number. So now we've got a dining room that measures 5 meters by 4 meters. And we have to be careful of the language in the next sentence. A strip of uniform width is added to 2 adjacent sides to increase the area by 5 meters squared. So that word adjacent just means 2 sides that are touching each other. So 2 sides that meet at some sort of vertex point or corner of the room. And then we want to find the width of this strip to 1 decimal place. So essentially, let's think about this. If this is the original space that we're dealing with, let's say this is the original dining room. Well, then we're told that its longer side is 5 meters and its shorter side is 4 meters. It's 4 by 5. And then we have a uniform strip that's added to 2 adjacent sides. So that could be something like this. And so those 2 adjacent sides essentially are the top, in my diagram, are the top side and the side to the far right. And I've added a strip that has a certain width to it. And that width is what I'm going to define this off to the side. I'm going to call that my variable. That's going to be our x. And that word uniform, when we say it's a strip of uniform width, it means the same width that it has on top is going to be the width that it has on the side. So that's going to be x units as well. So then we can think a bit more generally about the overall shapes that we see. If we want to think about this new longer length, it's not just 5 meters anymore. It's going to be 5 meters plus an extra x meters. This side here is not just 4 meters anymore. It's going to be 4 meters plus an extra x. That's how many extra meters it's going to be. But it's still, remember, going to be each of these values represented in meters. Beyond that, we're also told, and we'll use this for our calculations, that we want to increase the area by 5 meters squared. So first let's define that new variable and what this new x is representing. Before we use it in any calculations, I'm going to say let x represent the width of the uniform strip. And then if we can just find a way to solve for x, we'll have our actual value for the width of the uniform strip. Simple as that. So, in general, area of a rectangle, of course, equals length times width. What we want to do now then is try and use x that we just came up with. And so these x's are not part of the smaller rectangle that we started with, they're part of the larger rectangle that we created when we added the strips. So really, we want to create a formula that involves the final area and relates it to the final length and the final width. And by final length and final width, by that I mean the 5 plus x and the 4 plus x that we just defined previously. But the question is, what is this new final area going to be? Well, originally, we know that the original area must be, well, 5 meters times 4 meters, it must have been 20 meters squared. And the question says that this extension should increase the area by 5 meters squared, an extra 5 meters squared. So that means our final area, once we add these pieces on, should be 25 meters squared when we add an extra 5 meters squared. So let's put all of that together now. So now we can say 25 meters squared must be equal to 5 plus x for the new final length and 4 plus x for the new final width. And now you can see we're working towards a quadratic. This is a quadratic equation, but if we want to be able to use quadratic formula to help us, we need to expand it out and put it into standard form. So 20 plus 5x plus 4x plus x squared. Then I'm going to combine some terms and rearrange it into standard form. So eventually in standard form, we would get it down to x squared plus 9x minus 5. So once again, this is where I'm going to leave you to finish this one off because it really is just quadratic formula. So you can practice using quadratic formula with an a value of 1, a b value of 9, and a c value of negative 5. So finish that one off on your own. And you find potentially different values for x, but once again, we need to recognize which possible values of x are admissible or allowed, and if something is a negative value, we know that it is not allowed. It will be inadmissible, so keep that in mind. So take some time to try and finish that one off, and check your results using the completed version of the note. This example is similar to the previous one, but sort of doing things a little bit backwards. So now we have a specific space or a lot that we're using, and we're actually cutting down part of it. So in this case, a uniform width boardwalk is built around the inside edge. So that's what I mean by we're cutting down some of the space. We're using some of the total space we have inside of it. So built around the inside edge of a rectangular park that measures 15 meters by 10 meters in total. If the boardwalk takes up 20% of the lot, how wide is the boardwalk to the nearest centimeter? So again, the idea is that originally this thing was 15 meters by 10 meters. And then on the inside of it, they are building a boardwalk going around the outer edges. So we end up with something on the inside that looks roughly something like this. And then we need to think, how can we label the length and width of our new sides inside? Well, the boardwalk is going to have a width that is uniform once again. So this space here is going to be the same distance as this space and this space and this space. And that's also the thing that we're being asked to find. So once again, I'll define it over to the side in just a second, but that is going to be our variable. We're going to let x represent that uniform width that we're looking for. And that means we have this x width all the way around. So if we want to think about this distance inside, it started as 15 meters, but we've taken away an x from here, and we've also taken away x meters from this side. So we haven't just taken away x meters, we've taken away 2 copies of x. That's how many values of x we've taken away. So it's 2 x's being taken away in that case, and that's how many meters are left over. And a similar thing happens with this dimension here. It started as 10, but we take away an x from each side, so we take away 2x. So now we have this inner shape, the part of the park that does not contain the boardwalk around it, so the inner portion, and now we have a length and a width for that inner portion, that inner lot. So let's define our variable. We used x to represent the width of the boardwalk. But now as we go further, we need to think about what sort of areas are we really dealing with here. Well, we're going to try and create an equation based on the inner area, the area that's left over once we get rid of all that boardwalk space. So in general, we know that area is length times width. So that means the area on the inside, this inner area, must be equal to the length of that inner portion multiplied by the width of that inner portion. So those would be the values that I highlighted there in red in our diagram. But we need to substitute something in for the actual area of that inner portion, and we can figure out what that is. So first of all, we know that the area of the entire lot is 10 by 15, or in other words, it must be 150 meters squared. And we know that the boardwalk is taking up 20% of the lot. So that was something that was mentioned here. So the boardwalk takes up 20% of the lot. So what does that mean? Well, 20% of the area of our entire lot would be like doing 0.2 for 20% multiplied by our total area of 150, or in other words, the boardwalk is taking up about 30 square meters. But that's what the boardwalk is taking up. So that means the actual inner area that we're interested in must be 150 minus that, or in other words, 120 square meters. So that tells us, again, that the area of the inner portion, not including the boardwalk, is 120 meters. So let's use the equation that we defined before, this one in general, and let's set it up. I'll use the space that I have here. When I say 120, then, that inner area must be equal to the inner length, which is 15 minus 2x, times the inner width, which was 10 minus 2x. And once again, you can see we end up with a very similar situation to what we had before. So it is a quadratic equation. We just need to expand it out and get it into standard form so that we can use quadratic formula for it. So I'll do a quick expansion to help you out and get you on the right track. And when I rearrange a little bit, we have 0 equaling 4x squared minus 50x, minus 50x plus 30. Once again, that tells us what our a, b, and c values are. And I now leave it to you to once again put those values into quadratic formula and see what you get. And so in this case, because the question is just asking to the nearest centimeter, and all these values are in meters, what you're actually going to find first is a value in meters. But then if you round it off to just 2 decimal places in meters, you can convert that into centimeters.